Welcome to the Deep Dive. This is the show where we take a stack of sources, could be articles, research papers, you name it, and really pull out the most important stuff, the surprising insights, just for you, our listener. Think of it as your shortcut to getting up to speed.
Exactly. We do the digging, figure out what matters, and explain, so what behind it all.
And today we're diving into one particular source. It's a research paper with, let's say, a very descriptive title.
It is quite a mouthful.
It's called Assessing European Supply Chain Configurations for Sustainable Power to Polyethylene Production from CO2 and Renewable Electricity.
Phew. Yeah, but what it's looking at is incredibly important. Basically, how can Europe make polyethylene, that's PE, a super common plastic sustainably? It digs into different ways of setting up the supply chain using CO2, renewable electricity, checking the costs, and the climate impact.
Okay, right. So let's unpack that. We all know plastic is everywhere, but what's the core sustainability challenge here? Why is this such a focus?
Well, it goes right to the heart of the chemical industry. It's absolutely massive, vital for, well, everything modern, but it's deeply tied to fossil fuels.
Not just for energy, right?
No, that's the critical point. It uses fossil fuels for the huge amounts of energy it needs, yes, but also as the raw material, the actual building blocks the feedstocks.
Ah, okay. So it's not just the smokestacks at the factory, it's the carbon in the plastic itself that originally came from oil or gas.
Precisely. And this study points out that carbon, the fossil carbon embedded in the plastic, eventually gets released back into the atmosphere, maybe when it's burned, maybe other ways. So if the EU is serious about hitting its climate neutrality goals by 2050, it can't just clean up the energy used by the chemical plants. It has to change where the carbon for the chemicals comes from, too.
And this isn't a small slice of the emissions pie, is it?
Not at all. The study notes the chemical sector is the third largest source of greenhouse gas emissions in the EU.
Wow, third largest.
And globally, back in 2020, chemical production churned out something like 925 million tons of CO2 equivalent. Yeah. So tackling this, absolutely essential for climate action.
Okay, a huge industry, huge emissions. So within that, why the specific focus on polyethylene?
Because PE is just enormous in scale.
Yeah.
Its starting point, ethylene, that's C2H4, is the single most produced chemical in Europe. We're talking 19.4 million tons consumed back in 2021.
19.4 million tons.
Yeah. And polyethylene is where most of that ethylene goes, about 63%. It's in your packaging, pipes, films, just countless things.
Right. Impossible to avoid. And currently, how do we make all that ethylene and PE?
Mostly through a process called steam cracking. And the feedstock for that, overwhelmingly fossil fuels. Naphtha, which comes from petroleum, was like 68% of the feedstock for European steam crackers in 2020. Deeply fossil-based.
Okay, challenge established. Massive fossil-dependent process needs a green makeover. So what's the main solution this study looks into?
The paper really focuses on what they call electricity-based polyethylene, or EPE. They see it as a key way forward, alongside maybe using biomass, to defossilize PE production in Europe.
Electricity-based plastic. How does that work? Sounds a bit futuristic.
It's part of this whole emerging field called power to chemicals. What this study specifically models is the methanol to olefins route, MTO. The basic idea is you use renewable electricity, hopefully lots of it, to split water. That gets you green hydrogen.
Right, electrolysis.
Exactly.
Yeah.
Then you take that hydrogen and combine it with CO2 that you've captured sustainably, either from, say, an industrial source or even straight from the air.
Okay.
That reaction makes methanol, electricity-based methanol, or e-methanol. Then you take that e-methanol and convert it into olefins like ethylene. And then finally that ethylene becomes polyethylene, EPE.
Got it. So green power hydrogen, grab CO2, make methanol, make ethylene, make plastic. That sounds like it needs a lot of electricity.
Oh, absolutely. It's a huge energy shift. The study actually highlights that if you wanted to fully defossilize the entire European chemical industry this way, it could potentially double the continent's total electricity demand compared to 2020 levels.
Double Europe's electricity use, just for chemicals.
Potentially, yes. That figure really drives home the scale of the renewable energy build-out that's needed to support this kind of transition.
No kidding. So how did the researchers actually, figure out the best ways to do this in Europe? What was their method?
They developed a pretty detailed techno-economic model, and they paired that with a life cycle analysis, an LCA, to look at both the costs and the environmental footprint. And they focused on 4 specific European regions: Germany, the Benelux countries, Belgium and the Netherlands grouped together, B&L, Spain, and Finland, kind of covering different energy situations.
And they looked at different ways this could actually work in practice, different supply chains.
Exactly right. They didn't just model one setup. They assessed 7 distinct supply chain configurations for making this EPE. And they compared all of them to the way we do it now, the conventional fossil naphtha steam cracking.
7 options. Like what? All made locally.
That was one option, yeah. Fully local production within one of those European regions. But they also looked heavily at imports.
Imports. So making the plastic using green power, but maybe not in Europe.
Or importing parts of the process.
Yeah.
They modeled importing the green hydrogen, the EH2, from places expected to have really cheap renewables.
Yeah.
Morocco and Chile were the examples used in the study. Then Europe would just do the final steps to PE. They also looked at importing the green methanol, the EAEOH, from Morocco or Chile. So Europe would do the MTO step in the PE synthesis. And then the final option, just importing the finished EPE plastic directly from Morocco or Chile.
Okay, so local, import hydrogen, import methanol, or import the final plastic, quite a range, and they looked ahead into the future.
Yep. The model used 2020 as the baseline, but then projected costs and emissions out to 2030, 2040, and 2050, trying to account for technology getting better, energy prices changing, that sort of thing.
And the Ca2, carbon atoms, where do they assume that comes from?
Good question. For most of the scenarios, they assumed direct air capture DAC, machines literally sucking CO2 out of the ambient air.
Which is pretty energy intensive itself, right?
It is, yeah. But for Finland, they included a really interesting alternative, using point source capture, PSC, from the pulp and paper industry there. The idea is that this CO2 is sustainable biogenic carbon. It came from trees relatively recently, not fossil fuels dug up from the ground.
Ah, clever. Using an existing sustainable stream. Okay, so they've mapped all this out. Regions, timeframes, supply chains, CO2 sources. What did they find? Let's hit the economics first. Can this green plastic actually compete on cost?
Okay, so the big techno-economic headline from this study is, yes, EPE can become cost competitive with fossil PE, especially looking out towards 2040. But, and this is a really important but, often that competitiveness relies on having some form of carbon pricing or greenhouse gas pricing in place.
Ah, right. Making the dirty option more expensive helps the clean one compete.
Essentially, yes. Policy is key there.
Did they give any specific cost targets, like for the hydrogen?
They did. They calculated that to get the cost of the resulting ethylene down to roughly where fossil ethylene costs are today, about 631 euros per ton, they estimated you'd need the input green hydrogen cost to be somewhere around 27 euros per megawatt hour.
27 LW for hydrogen. That's a benchmark to aim for. How did the costs look across the different European regions if they tried to produce the EPE locally?
Well, there's a pretty big spread in the projected local production costs, or EPE, by 2050, ranging from about 712 euro up to 1,406 per ton.
That's almost double at the high end. Which region came out looking best for local production?
Spain really stood out in the results. Because of its potential for very low-cost solar power, Spain showed the lowest projected costs for making EPE locally. The study even suggests Spain might reach competitiveness with fossil PE by 2050 without needing really aggressive carbon pricing, just based on that solar advantage.
Interesting. Spain's sunshine as a chemical feedstock advantage. What about Germany, Benelux, Finland?
Their local costs were projected higher. For Finland, using that pulp mill CO2, the point source capture did help. It lowered their costs by about 10–12% compared to using just direct air capture. But even with that boost, the study found it likely wasn't enough to make local Finnish production competitive against importing from places with potentially rock-bottom renewable energy costs.
Right. Which leads us straight to the import options. How do they stack up economically? Hydrogen first.
Importing the green hydrogen, EH2. That consistently looked like the most expensive route for Europe in their models, significantly pricier than local production or importing other things. By 2050, they projected imported EH2 pathways could cost anywhere from 119% to 235% more than local production. The main reason, transporting hydrogen is just really difficult and costly, whether by pipeline or ship.
Yeah, heard that before. Hydrogen's tricky to move. Okay, what about importing the methanol instead?
Now this is where things got really interesting in this study. Importing the e-methanol, the EMAOH, looked like a much more competitive strategy. By 2050, its cost was projected to be somewhere between 56% and 118% of local European production costs, so potentially cheaper, or at least in the same ballpark. Shipping EAAH, especially from a place like Chile with projected super low hydrogen costs, seemed particularly promising economically.
And the advantage there is?
Well, you get to benefit from the low-cost green hydrogen made elsewhere, but you keep the more complex, higher value-add steps converting methanol to olefins, and then to PE actually in Europe. You keep that part of the value chain, the jobs, the tech know-how closer to home.
Okay, so importing the intermediate makes sense. What about just importing the finished product, the EPE plastic itself?
That option, importing the final EPE from, say, Morocco or Chile, actually showed the potential for the absolute lowest production cost globally in many of their scenarios, ranging from just 42% up to 108% of the cost of local European production by 2050.
42%. Wow, that sounds like it could really undercut European production, even Spain's.
It definitely could pose a challenge, yeah. But the study also points out, look, Europe already imports a lot of primary plastics. So you could argue that importing EPE would just be substituting existing fossil imports with sustainable ones. It really frames a strategic choice for Europe. Do you go for the absolute rock-bottom cost by importing the finished goods, accepting the value chain shifts largely outside the EU? Or do you maybe pay a slight premium to import the methanol and keep more of the manufacturing process within Europe?
That's a huge strategic question. Economics versus industrial strategy, almost. Okay, let's pivot from cost to climate. How much greener is this EPE? What did the life cycle analysis show?
The LCA results were pretty positive, especially for local production. Making EPE fully within Europe showed significantly lower greenhouse gas emissions compared to the traditional fossil PE route. The reductions ranged from 15% up to a really quite substantial 61%, depending on the region and the year they were looking at.
61% lower emissions. That's a major climate win.
It really is, and the study even touches on this idea of a potential negative carbon footprint.
Negative. How?
If you consider the carbon that's physically stored in the plastics,
Okay.
remember it came from CO2 captured from the air or from those trees via the pulp mill.
Ah, so the plastic itself becomes a form of carbon storage.
Kind of, yes. But, and this is the really crucial caveat they stress, that only holds true if the plastic doesn't end up releasing that carbon back later. If it's incinerated and end of life without any carbon capture on the incinerator, poof, the carbon's back in the atmosphere. So while the storage idea is interesting, the main guaranteed climate benefit they highlight is from slashing the emissions during the production itself.
Got it. Focus on cleaning up the making of it. What's the biggest emission source within the EPE process chain?
By far, the study identifies the electricity used for the water electrolysis making the hydrogen. That step alone accounts for something like 64% to 94% of the production emissions.
Wow, nearly all of it in some cases.
Yeah, it really underscores how critical truly clean electricity is for this whole concept to deliver on its climate promise. CO2 capture and transport emissions are also factors, but electrolysis power is the big one.
Did the climate impacts vary by region too, like the costs did?
They did. Interestingly, the region with the lowest projected emissions for local EPE production was actually the Benelux area, BNL. The study suggested this was due to a higher share of wind power assumed in their future energy mix, which apparently had lower upstream emissions in the database used compared to solar.
So Spain had the lowest cost, but maybe not the absolute lowest emissions.
Exactly. Spain's local EPE emissions were projected slightly higher than BNL's from 2030 onwards. The study attributed this to the specific assumptions in their LCA database about the emissions baked into manufacturing. Lots of solar panels needed for Spain's 100% solar scenario. A bit of a nuance there.
Interesting detail. And how did transport affect the emissions for the import routes?
Transport definitely matters for emissions too. For some import scenarios, especially those involving very long distances, like pipeline transport of hydrogen or methanol all the way to Finland, the transport emissions could actually push the total production footprint higher than even the old fossil PE pathway.
So importing isn't automatically cleaner?
Not necessarily, especially if transport is inefficient or over huge distances. Other import routes were cleaner than fossil PE, but generally the lowest cradle-to-gate emissions in the study were found in the local European production scenarios. They also added a small note, a limitation, saying their LCA didn't really factor in future improvements in how clean the manufacturing of wind turbines or solar panels themselves might become. So future EPE emissions could potentially be even lower than shown.
Okay, so putting it all together, the economics, the climate impacts, what are the big implications here? The main takeaways for Europe's chemical industry looking ahead?
Well, I think this study really hammers home a couple of key points. First, that carbon pricing, or some kind of GHG pricing, looks pretty essential, at least in the medium term, if EPE is going to compete fairly with the incumbent fossil stuff.
Policy matters.
Hugely. Second, it just screams that access to abundant, affordable, clean electricity and the resulting feedstocks like green hydrogen or e-methanol is absolutely make or break for this whole power to chemicals vision in Europe.
And Spain seems particularly well placed for local production because of its solar resources.
Exactly. Spain has a potential unique advantage there. But for other parts of Europe, maybe central, northern regions where land for massive renewables might be scarcer or local renewable costs higher compared to, say, North Africa or South America.
Imports start to look more attractive.
That's what the study suggests, yes. Especially importing e-methanol seems like a potentially very strong economic play for those regions. Or maybe even importing the final EPE, despite the value chain implications.
Right, bringing us back to that core strategic dilemma. Import the intermediate methanol to keep some industry local, or import the finished good, PE, for potentially the lowest cost.
That seems to be the central strategic question highlighted by this research. And whichever path or mix of paths Europe chooses, the investment needed is just staggering. We're talking colossal amounts of new renewable energy, huge scale-up of electrolyzers, CO2 capture tech, pipelines maybe, new synthesis plants, a massive industrial transformation.
Did the study mention things it didn't fully explore but could be important?
Yeah, they flagged a few areas for more work, like developing better intra-European connections, maybe a hydrogen backbone pipeline across the EU to move these feedstocks around internally. Also, making better use of the waste heat from electrolysis. That process generates a lot of heat. Could it be used for district heating, especially in colder places like Finland? That could improve the economics. Right. And using existing industrial sites, brownfield development, instead of building everything new. Plus, they noted needing better data on regional financing costs, the WACC, which really influences investment decisions.
And this whole shift isn't happening in a vacuum, right? It's global.
Absolutely. You have to see it globally. The study points towards the rise of new potential global hubs for producing these e-chemicals based on where renewable energy is cheapest. That have big geopolitical implications for who Europe might depend on for its future chemical feedstocks. It could really redraw the map of chemical trade.
Beyond carbon pricing, did they mention other policy tools?
Briefly, yeah. Things like maybe specific carbon credits for locking CO2 into these long-lasting plastics, or perhaps taxes on fossil-based plastics to nudge the market towards these greener alternatives. Standard policy toolkit ideas.
It really sounds incredibly complex. You're weaving together technology, economics, climate science, policy, global trade.
It is definitely complex, but what this study does is provide a really valuable, detailed map of the potential routes forward. It lays out the likely costs, the climate benefits, and flags those crucial strategic choices Europe needs to grapple with as it tries to defossilize something as fundamental as plastic.
Okay, so wrapping up our deep dive into assessing European supply chain configurations for sustainable power to polyethylene production from CO2 and renewable electricity, the core message seems clear. Making Europe's PE sustainable means a massive shift away from fossil inputs towards captured CO2 and renewable power. This study shows local production looks promising, especially where renewables are cheap, like Spain. But for other parts of Europe, importing intermediates like e-methanol or maybe even the final EPE could be key. It really hinges on low-cost green power and efficient transport.
And crucially, the policy decisions and the investment choices happening right now are going to heavily shape which path Europe actually takes.
Absolutely. Which leaves us with a final thought for you, our listener, to chew on. Given all these complexities, the supply chain choices, the fluctuating energy costs worldwide, the global competition that the study highlights, what factors, maybe beyond just the tech and economics we discussed, do you think will ultimately decide where Europe gets its sustainable plastics from in the future?
Yeah, something to think about as this huge shift plays out.
Indeed. Thanks for joining us for this deep dive.
My pleasure.